Welcome back to the deep dive. Today we are peering behind the curtain of one of the most fundamental yet, least understood forces governing our world. We're talking about the invisible dance of vapor equilibrium and vapor pressure. And this isn't just theory for a physical chemistry exam. This is the physics that dictates everything from, massive global power generation cycles to why you feel absolutely miserable on a humid summer day.
It really is. It's the invisible force that links the random motion of individual molecules to global climate patterns and industrial efficiency. Our source for this deep dive is a technical text, Verdampfungsgleichgewicht und Dampfdruck, by Matthias Schulze and Peter Seidel. It's a very concentrated, dense exploration of the essentials.
And our mission today is to give you a comprehensive shortcut. We are going to move straight from the foundational thermodynamic theory through the clever, often historically challenging experimental methods, and finally right into the crucial real-world applications in nature and technology. We promise that by the time we're done, you'll have those serious aha moments that show how this simple piece of physics governs your entire everyday reality.
I think so. If you've ever wondered what makes a turbine spin, how your refrigerator keeps food cold, or why sweat sometimes works and sometimes doesn't, the answer is locked within the principles of vapor pressure. So I think we should start by just mapping the world of matter.
Okay, let's unpack this, starting with the very basics, the concept of phase transitions. We all learned pretty early on that matter has three classic states: solid, liquid, and gas. But these states are always connected, right? They're always moving between each other.
Precisely. The core text walks us through the classic phase changes. You've got melting and freezing, which is the solid-liquid transition, evaporation and condensation, that's liquid gas, and then sublimation and resublimation, solid gas. And these transitions aren't continuous processes. They are abrupt, discontinuous changes in a substance's fundamental properties.
You things like its volume.
Its volume, its entropy, how it holds heat. When a substance undergoes a phase change, the molecules rearrange fundamentally.
And we can map all of these states perfectly. And that brings us to the PT diagram, which you called the universal map of matter.
The PT diagram is just a powerful visualization tool. It illustrates the state of any pure substance based entirely on two external parameters. Pressure, which we call P, and temperature, T. The lines drawn on this diagram, the vapor pressure curve, the melting pressure curve.
On the sublimation curve, right? All on one map.
Exactly. And those lines represent all the points where two phases can coexist in a stable thermodynamic equilibrium.
And when a system is sitting right on one of those lines, the Gibbs phase rule defines it as univariant. Wait, univariant. That's a bit of jargon. Break that down for us. What does that actually mean for the stability of the system?
It's a good question. It means the system has only 1 degree of freedom. Think about boiling water at sea level.
Okay.
We know the pressure is fixed at 1 atmosphere and the temperature is fixed at 100 degrees Celsius. If you try to change the temperature up to, say, 101 degrees, the liquid immediately vanishes. You just move into the single-phase gas domain.
Ah, I see.
So if you want to maintain that equilibrium, keeping both liquid water and steam present, you can only change one variable. Let's say you decide to raise the temperature. Well, the pressure must instantly rise to a new fixed value to keep that balance. The variables are yoked together.
And this is where it gets really interesting, these critical landmarks on the map. First, the incredibly delicate triple point.
The triple point it's the single, unique coordinate of pressure and temperature, where all three classical phases, solid, liquid, and gas, can coexist in perfect dynamic balance.
It's a state of immense fragility, then.
It is. For water, this occurs at precisely 612 pascals and 273.16 Kelvin.
Which is, for reference, just 0.01 degrees Celsius.
Right. And if you change that value even slightly, a single pascal or 1/100th of a degree, the system immediately collapses into one phase or shifts toward the boundary line between two phases. It's a perfect bullseye.
So it's incredibly precise.
It is. In fact, that exact temperature point is often used as a standard reference for calibrating high-precision thermometers globally, precisely because it is so rigorously fixed and reproducible.
Okay, so then you have the opposite end of the curve, the critical point. This always felt like some kind of theoretical maximum to me, but what does it really represent physically? Is it useful?
Oh, absolutely. The critical point is the highest temperature and pressure at which a liquid and its vapor can coexist. It marks the end of the vapor pressure curve. Above this specific coordinate, the molecular density of the liquid and the gas become equal.
And the distinction between the two phases just completely vanishes.
It vanishes. So it's not a liquid and it's not a gas. It's something entirely new.
A new state of matter.
Exactly. It enters this unique fluid state called a supercritical fluid. For water, this happens at a staggering 22 megapascals.
Wow, that's about 220 times atmospheric pressure.
It is. And 647 Kelvin, or 374 Celsius. The key physical concept is that above that critical temperature, you can apply infinite pressure, but the substance will never condense back into a recognizable liquid.
And this isn't just academic. That supercritical fluid state is what gives engineers those important industrial applications we mentioned earlier.
It certainly does. Supercritical fluids exhibit properties of both liquids and gases. They can diffuse through solids like a gas, but they can dissolve materials like a liquid.
That's a strange combination.
It is. Supercritical CO2, for instance, is used all the time in industrial decaffeination. It acts as an excellent solvent without the harshness of organic solvents, and its solvent power can be fine-tuned just by adjusting the pressure and temperature. That's a powerful tool derived directly from this landmark on the phase diagram.
So let's pull the lens back and look at the microscopic mechanics driving all of this, starting with the liquid phase itself.
Yeah, we need to visualize the liquid at the molecular level. In a liquid, the atoms or molecules are close together, much closer than a gas, so they maintain some fleeting short-range order.
But not the rigid, long-range order of a crystal.
Right. And crucially, they are in constant, non-periodic, random motion due to thermal energy. This is Brownian molecular motion.
And these molecules are just constantly colliding, shuffling energy back and forth.
Absolutely. Those collisions continuously redistribute kinetic energy among the particles, and it follows a statistical distribution. So at any given moment, most particles have an average energy related to the bulk temperature, but a small, high-energy fraction is moving much faster, and a low-energy fraction is moving much slower.
So how does vapor pressure form from that microscopic chaos?
It's purely statistical. Only those molecules that happen to be near the surface and through random collisions have gained sufficient kinetic energy.
Enough to break free.
Enough energy to overcome the collective intermolecular attractive forces, like hydrogen bonds, van der Waals forces, that hold the bulk liquid together. Only those are able to escape into the gas phase.
And that concentration of escaped high-energy molecules floating just above the liquid surface, that's what generates the vapor pressure.
Correct. But this is a dynamic process. It leads to the fundamental concept of equilibrium. While high-energy particles escape to form vapor, slower-moving particles in the gas phase can be captured by the liquid surface and re-enter. That's condensation.
So vapor pressure is reached when the rate of escape from the liquid equals the rate of re-entry from the gas. It's like a war fought to a constant standstill.
A perfect description.
That makes equilibrium a very specific, isolated condition. But in everyday life, we usually talk about evaporation, or as the source calls it in German, Verdunstung. That's a bit different, isn't it?
It is a critical distinction. Evaporation, or Verdunstung, occurs when this perfect, isolated equilibrium is disturbed. Most commonly, this disturbance is caused by air circulation, or a constant flow of gas moving over the liquid surface.
So by sweeping the air, you're constantly removing the escaped vapor molecules.
Exactly. The vapor concentration above the liquid drops, so the vapor pressure becomes smaller than the total gas pressure. Because the rate of reentry or condensation drops sharply, the liquid is forced to continually shed molecules faster than it absorbs them.
And that ongoing non-equilibrium process, which requires an external energy supply, is the evaporation we see every day, like a puddle drying up.
Or sweat cooling your skin, exactly.
And if you keep heating a liquid until its vapor pressure equals the external pressure like atmospheric pressure, you get to the point where particles are moving so vigorously that they can overcome intermolecular forces, not just at the surface, but throughout the entire bulk of the liquid. And that is boiling.
That's boiling, where the phase transition happens en masse. And that transition is so rapid and energetic that it has its own costs and consequences. Which brings us to the next point. The energy required to make this transformation happen.
Right. When you look at boiling water, you keep pumping thermal energy into the stove, but the temperature gauge just sits stubbornly at 100 degrees Celsius. Where is all that energy going?
It's being stored as latent heat. The thermal energy you supply isn't increasing the kinetic energy, the temperature of the liquid molecules. Instead, that energy is used solely to increase the potential energy of the molecules.
To break them apart.
To overcome the intermolecular forces necessary to separate them and change the state from liquid to gas.
And this stored energy is a physical danger, right? This is why steam burns are so much worse than boiling water burns.
Absolutely. The energy is stored within the vapor phase. When that steam touches your cooler skin, it instantly condenses back to liquid water, releasing all that massive amount of latent heat directly onto your tissue. It's a highly effective, rapid, and destructive energy transfer.
The technical term for this specific quantified energy input, this cost of liberation, is the enthalpy of vaporization, or AVH.
Right. AVH is the specific energy required for evaporation at constant pressure and temperature, usually expressed in kilojoules per mole. Because you must always add energy to break those cohesive forces and turn a liquid into a gas, evaporation is always an endothermic process. AVH is always positive.
And you can calculate this.
Yes, we can calculate this value for a substance, like ethanol, using Hess's law, if we know the standard formation enthalpies of both the liquid and the gas phases. We just take the difference. It allows chemists to quantify the strength of the bonds holding the liquid together.
So that's the energy cost. What about the change in order, or entropy, yes? We talked about disorder earlier.
Entropy is fundamentally a measure of the disorder, or the number of energetically equivalent microstates available to the system. When a liquid vaporizes, the molecules go from being confined and interacting closely to being virtually independent and occupying a massive volume.
A huge increase in freedom.
A huge increase in positional freedom and thermal disorder. It's a massive entropy gain, so BVS is always positive.
Is there some kind of universal rule for how much disorder we should expect?
Well, our source mentions an empirical approximation known as Pictet-Troughton's rule. It suggests that the molar entropy of vaporization for many nonpolar liquids is roughly constant, around 88 to 90 joules per mole Kelvin.
So the increase in disorder is surprisingly consistent.
For many simple liquids, yes. The rule is incredibly useful for estimation, and it highlights that while the energy cost, AVH, varies wildly between substances, the increase in disorder upon vaporization is pretty consistent.
And this entire concept of storing and releasing energy during a phase transition has some brilliant, large-scale applications in engineering. Let's talk about latent heat storage.
This is becoming crucial for modern energy management, especially when trying to balance the intermittent nature of renewables like solar or wind. Traditional energy storage, like heating a tank of water, uses what we call sensible heat. The temperature just increases proportionally to the energy added.
But latent heat storage uses the phase change itself.
Exactly. It often utilizes the solid-liquid phase transition as it's easier to contain than the liquid-gas one. Materials known as phase change materials, or PCMs, absorb a vast amount of heat when they melt, often at a very specific, useful operating temperature.
And then when they re-solidify,
they release that stored energy steadily and consistently back into the system.
It's a way to hoard energy at a constant temperature, like those great little hand warmers we all used as kids that you click to turn hot.
That's a perfect microcosm of the technology. They typically use sodium acetate trihydrate. You heat the material until it melts, absorbing and storing latent heat. When you initiate crystallization by clicking the disk, that stored energy is released over a longer period, providing steady warmth without the temperature immediately skyrocketing and then dropping.
It's just a really clever way to manage energy flow.
Very effectively and consistently, yes.
Okay, now we move from the observation of phase transition to the mathematical core that predicts it. We need to derive the master equation, the Clausius-Clapeyron equation. It sounds incredibly dense, but it is arguably the single most important equation for understanding any vapor pressure curve.
It is. It connects four fundamental measurable quantities: pressure, temperature, volume, and enthalpy in one clean relationship. We start with the fundamental condition for equilibrium. The chemical potential, Claire, of the liquid phase must equal the chemical potential of the gas phase. So camel equals big.
Hold on, let's define chemical potential again. Why is this the right tool to measure equilibrium?
The chemical potential is essentially the molar free energy. It tells us the system's inherent ability to do work, or more simply, the tendency of a substance to escape its current phase.
So if the tendency to escape the liquid is equal to the tendency to escape the gas, you have a perfect balance.
Equilibrium, exactly.
So if we're tracing the vapor pressure curve, we are looking for how tiny infinitesimal changes in temperature dT and pressure dP still satisfy that perfect equality.
Exactly. If the system moves slightly along the curve, the change in chemical potential for the liquid, dl, must equal the change for the gas, gag. And by manipulating the fundamental Gibbs equation for free energy, we find that the change in chemical potential is dependent on the change in molar entropy, S, and molar volume, V.
So you get this equation, NaSSL dt plus VLdP equals dash SG dt plus VGdP. That looks like a mess of variables, but I can see how it leads to the Clapeyron equation.
The beauty is in the rearrangement. If you group the temperature terms and the pressure terms, you can solve for the slope of the curve, dp dt, and you find that it equals the change in entropy divided by the change in volume,
which is EVS over LV.
And we already know that at the phase transition temperature T, the change in entropy is related to the latent heat, the enthalpy of vaporization, EVH. So we can substitute that in, and we arrive at the perfectly general Clapeyron equation, dp dt divided by T times EVV.
That is genuinely elegant, and the immediate physical insight from it is powerful.
It is. Since AVH, the energy added, and AVV, the volume expansion, are almost always positive for vaporization, the entire ratio must be positive. Therefore, the vapor pressure curve always has a positive slope. Pressure must rise with temperature. We had that intuition, but this equation proves it mathematically.
But as elegant as the Clapeyron equation is, it's a little clunky for practical use, right? Because measuring that small liquid volume change accurately is difficult.
It is, especially as temperature changes, which is why we introduced two approximations that simplify it into the tremendously useful Clausius-Clapeyron equation. We assume we are far enough away from the critical point that 1, the volume of the liquid phase is negligible compared to the volume of the gas phase.
So AVV is pretty much just VG.
And 2, we assume the vapor behaves like an ideal gas, meaning we can substitute the ideal gas law into the volume term.
Wait, why is assuming ideal gas behavior acceptable here? I mean, doesn't the source acknowledge that real mixtures deviate from that?
It's a simplifying assumption, but it's good enough for small temperature ranges and moderate pressures. If the gas isn't too dense, so not close to condensation or the critical point, the interactions between the gas molecules are minor, and the ideal gas law approximation holds surprisingly well. It allows us to substitute the volume term out, transforming the equation into its powerful differential form.
And here's the crucial practical takeaway, which is known as August's formula. If you integrate that differential equation, assuming, and this is another approximation, that AVH is constant over the measured temperature range, you get a simple linear relationship.
Is AVH RT plus C.
And the simple linear relationship is the key.
Yes. Plot the natural logarithm of the saturation vapor pressure against the inverse of the temperature, and the resulting graph is a straight line.
It transforms an exponential problem into a linear one. That's pure brilliance.
And the slope of that straight line is directly proportional to the negative molar enthalpy of vaporization. This means a simple experiment gathering pressure and temperature data, plotted this specific way, allows us to calculate the fundamental thermodynamic energy required to vaporize the substance.
This linearity is just one of the greatest tools in physical chemistry.
It really is.
We should briefly note the empirical equations used in heavy engineering, like the Antoine equation. It looks similar, but it uses 3 empirically determined constants to model the data, and it often provides a slightly better fit over wider temperature ranges.
Right, because it implicitly accounts for the slight temperature dependence of AVH that the simpler integration ignores.
Now, everything so far has dealt with a pure substance, but the real world is built on mixtures. What happens when you mix 2 liquids?
Well, you introduce complexity because you introduce competing intermolecular forces. We start with the simplest case, ideal mixing. This is purely theoretical, where the interaction forces between different molecules, A, B, are exactly the same as the forces within the pure substance, AA or BB.
So the forces are identical. The molecules don't care who their neighbors are.
Right, and this is best approximated only by very similar substances, like different isotopes of water, like H2O and D2O, heavy water.
And for these ideal scenarios, we use Raoult's law.
Raoult's law is beautifully simple. The partial pressure of a component over the mixture is the product of its mole fraction in the liquid and the vapor pressure of the pure substance. It basically says that if 50% of the liquid is molecule A, then 50% of the total vapor pressure will be due to molecule A.
And since the total pressure of the gas phase is just the sum of the partial pressures, Dalton's law, the total vapor pressure of an ideal mixture is a simple linear interpolation between the pure components.
Exactly. Plotting the total pressure against the mole fraction gives you a straight line. And this is the basis for understanding how easy it is to separate ideal mixtures.
But as we mentioned, the real world is messy. How do real mixtures deviate from this ideal linear behavior?
Real mixtures exhibit non-ideality due to differences in those critical intermolecular forces. We see 2 main types of deviation. First is positive deviation. This occurs when there are repulsive forces between the different molecules. The particles don't like being near each other in the liquid, so they escape more easily.
So the total vapor pressure is higher than predicted by Raoult's law.
Higher. The curve bows upward. A classic example is a water-toluene mixture. Then you have negative deviation. This happens when there are strong attractive forces between the different molecules. They form unexpected, stabilizing bonds in the liquid.
So it's harder for them to escape.
Much harder. This causes the total vapor pressure to be lower than predicted, and the curve bows downward. Acetone and chloroform do this because of hydrogen bonding.
So the non-ideal graph looks wavy, either bowing above or below that ideal straight line.
Right. And for serious engineering, Raoult's law has to be corrected using factors like the activity factor for the liquid and the fugacity factor for the vapor, which are just empirical corrections for these real-world interactions.
And before we move on, a quick note on gas solubility, like the bubbles in soda.
That's covered by Henry's law. It applies mainly to dilute solutions where a gas is dissolved in a vast excess of liquid. It relates the partial pressure of a gas above the liquid to its concentration in the solution via the Henry constant. This is key for manufacturing carbonated beverages, where high pressure forces CO2 into the liquid.
Okay, so if the Clausius-Clapeyron equation is our map, then the next question is how we gather the data points to plot that map reliably. Our source reminds us that the reliability of vapor pressure data depends entirely on accurate measurement of temperature and pressure.
That reliability is absolutely crucial. Historically, obtaining accurate PT pairs, especially at high temperatures where the sample could degrade or distill away, was a huge source of error. Smith and Menzies' work in the early 20th century was foundational because they managed to overcome these specific challenges.
Let's start with pressure. This goes back centuries, right, to the roots of experimental physics.
Indeed. The foundational principle was established by Evangelista Torricelli, a student of Galileo, who developed the mercury barometer. He was the first to recognize that atmospheric pressure supports a column of mercury up to about 760 millimeters. This led to the definition of the unit torr, named after him.
And in terms of actual measurement tools, we differentiate between direct and indirect methods.
Direct methods relate directly to the physical definition of pressure as force per area. The simplest example is the liquid column manometer, like the U-tube, where the pressure difference depends on the height and density of the liquid column.
And indirect methods.
Indirect methods rely on pressure changing some physical or electrical property, which is then calibrated. Examples include the deformation of a tube spring or the change in capacitance or resistance in digital pressure sensors. They offer high precision but need constant calibration.
And for temperature, the measurement choice is key to accuracy as well.
Of course. We use standard tools like liquid or gas thermometers for simple checks. But for high precision in the lab, we rely on resistance thermometers or thermocouples, which exploit the Seebeck effect.
So to determine the actual vapor pressure of a liquid, chemists use two main experimental philosophies, static and dynamic. What defines the static methods?
Static methods measure the pressure, P, when the temperature T is held constant. The system is completely sealed, and the liquid and vapor must be given sufficient time, often hours, to reach perfect equilibrium before the pressure is read.
And the classic apparatus in this category, and the one detailed in our source, is the isotenoscope. This device was revolutionary because it solved the problem of the sample distilling away.
Its design is truly ingenious. The sample liquid is placed in a closed, heated vessel. This vessel is coupled to an auxiliary U-tube manometer, and critically, this auxiliary manometer is filled with the sample liquid itself, separating the sample from the external, high-precision main manometer.
So how do you use the external manometer to read the internal vapor pressure?
You apply an adjustable external pressure to the reference side of that auxiliary U-tube. You slowly adjust this external pressure until the levels in the two arms of the auxiliary U-tube are perfectly equal.
And when the levels are equal, the pressure exerted by the sample vapor must precisely match the external pressure being applied.
Exactly. This setup effectively buffers the sample. The sample never touches the cold external gauge, which prevents distillation errors and ensures you get a clean reading of the sample's true saturation vapor pressure, even at high temperatures.
The alternative is the dynamic method, often called the boiling method.
Dynamic methods measure the temperature at which the liquid boils when the external pressure is held constant. By definition, the boiling temperature is the point where the substance's internal vapor pressure exactly equals that external pressure.
And the apparatus for this is often the ebullioscope.
Yes, the ebullioscope is specifically optimized for accurate boiling point determination, often under controlled, reduced pressure. The most critical feature is the setup around the thermometer. The rising hot vapors of the boiling substance continuously flush the thermometer bulb, surrounding it entirely.
Why is that so crucial?
Because if the thermometer were simply dipped into the bulk liquid, it might register a temperature slightly above the true boiling point. It's a phenomenon called superheating.
Ah, right.
By flushing the thermometer with the vapor, we ensure we're reading the temperature of the vapor in equilibrium with the liquid, guaranteeing an accurate reading of the boiling temperature at that specific pressure.
Beyond these, researchers sometimes need specialized methods, especially for hard-to-measure substances.
The gas saturation method is one such alternative. Instead of measuring pressure, we measure mass.
How's that work?
An inert carrier gas, like helium or nitrogen, is passed very slowly through the liquid sample until it is guaranteed to be fully saturated with the sample vapor. The vapor pressure of the sample dictates how much mass is carried off.
And then you just measure the mass loss over time.
Precisely. The amount of sample carried off is measured analytically. The saturation vapor pressure is then calculated by relating the amount of vaporized sample to the total volume of inert gas used with the ideal gas law.
And if you're studying solids or substances with extremely low vapor pressures, things that barely evaporate, that takes us into high-tech territory with the Knudsen effusion method.
This is a specialized research tool, primarily used for solids or high molecular weight liquids that require high vacuum. It relies on the physics of effusive flow.
Let's look inside the Knudsen cell. What's happening there?
The substance is placed inside a sealed cell with a tiny, precisely machined opening. The entire assembly is placed under a high vacuum. The goal is to create conditions for molecular flow, meaning the mean free path of the molecules is much larger than the diameter of the orifice.
So when a molecule escapes through that hole, it's doing so without colliding with any other molecules. It's a non-collisional particle beam.
Yes. And we're measuring the rate at which molecules effuse into the vacuum. You can either measure the mass loss over time, that's the Knudsen mass loss method, or you can analyze the effusing particle beam directly with a mass spectrometer, which is CHEMS. Both methods allow researchers to measure vapor pressures down to incredibly low values, often below a millionth of a Pascal.
Okay, if part 2 was the theory, this section is the massive payoff. Vapor equilibrium isn't just a lab curiosity, it's the engine driving vast industrial processes and vital natural cycles. Let's start with water.
Water vapor is a critical component in many technological systems, but for engineers, you have to be very precise about what kind of steam you're using because its energy content varies wildly. Our source details 5 distinct states of steam.
Let's break those down, starting from the baseline liquid.
Number 1 is just water, the liquid, temperature below boiling. 2 is wet steam. As heat is added, vaporization begins. This is a mix of liquid and gas in equilibrium. Critically, as long as the liquid is present, the temperature is constant. All energy input just increases the vapor content. 3 is saturated steam. This is the endpoint of the phase transition, 100% vapor, but still at the boiling temperature. This is used for sterilization and things like that.
Okay.
4 is superheated steam. Once it's all vapor, adding more heat increases the temperature above the boiling point. This scheme is dry, highly energetic, and necessary for driving large industrial turbines. 5 is supercritical water. This is steam beyond the critical point. It behaves as a dense, high-energy fluid. Power plants using this technology achieve extremely high efficiencies, but the water becomes incredibly corrosive.
And the conversion of this thermal energy into useful work is the purpose of the Clausius-Rankine cycle, which is the thermodynamic heart of every modern steam power plant.
The cycle's entire function is to convert the immense thermal energy stored in superheated steam into mechanical work and then electricity. It involves 5 core steps.
Okay, walk us through them.
First, you have compression. Liquid water from the condenser is compressed to a very high pressure. Second is isobaric heating and isothermal vaporization in the boiler. Immense heat is added at constant pressure to turn the water into saturated steam. Third is superheating. More heat is added to raise the temperature well above saturation, creating that dry, superheated steam.
And then it goes to the turbine.
Right. Fourth is isentropic expansion. The high-pressure steam expands rapidly through the turbine, converting thermal energy into kinetic energy, turning the blades. And fifth is isothermal condensation. The low-pressure spent steam is cooled and condensed back into liquid water, ready to restart the cycle.
So what's the thermodynamic secret that maximizes the work output and efficiency? It all comes down to the condenser, doesn't it?
It absolutely does. The efficiency of a heat engine like this is maximized by creating the largest possible pressure differential between the high-energy input and the low-energy output. When the steam is cooled and condenses back into liquid water, its volume dramatically decreases by a factor of maybe 1,600 times.
So that rapid volume reduction essentially vacuums the spent steam out of the turbine.
Precisely. This creates a nearly perfect vacuum within the entire low-pressure circuit, establishing a massive pressure differential that the turbine operates across. That maximum pressure drop means the steam exerts maximum force over the maximum distance, directly increasing the mechanical work extracted and, consequently, the efficiency.
So if a condenser failed to create that vacuum, efficiency would just plummet.
Immediately.
The power plant uses the cycle in one direction to turn heat into work, but we can run that exact same cycle in reverse to move heat from a cold place to a hot place. This is the reverse Carnot cycle, which underpins heat pumps and refrigerators.
These machines function by cleverly exploiting the phase change under controlled, variable pressure differences. The physical principle is this. Lowering the pressure of a substance lowers its boiling point, and increasing the pressure raises it.
Let's focus on the heat pump, whose goal is to heat a living space by taking low-grade heat from the cold outside. How does the working fluid leverage phase change?
The cycle has 4 key components, all centered on manipulating vapor pressure. First is the evaporator, which is located outside. The refrigerant fluid is at low pressure, so its boiling point is very low, maybe minus 10 Celsius. Even if it's 0 degrees outside, that's warm enough to make the fluid boil, and it absorbs heat from the cold environment as it vaporizes.
Okay, so it boils outside in the cold.
Then you have the compressor. This is where external work is inputted. The low-pressure gas is compressed, significantly increasing both its pressure and its temperature. Third is the condenser, located inside the house. The refrigerant is now a high-pressure, high-temperature gas. Its new high boiling point is now higher than the room temperature.
So it releases its latent heat into the living space as it condenses back into a liquid.
Correct. And finally, the throttle or expansion valve. The high-pressure liquid passes through a restriction, which drastically reduces the pressure, again, restarting the cycle in the cold evaporator.
And the genius is that the electrical work needed to run the compressor is much less than the total heat energy released indoors. You're not creating heat, you're simply moving it.
Exactly. Refrigeration is the same principle, but the focus is different. The evaporator sucks heat from the freezer compartment, and the condenser releases the waste heat into the kitchen.
Distillation is maybe the most ancient application of vapor equilibrium. It's been used for millennia to make spirits, but it remains vital today in things like oil refining.
It's a beautifully simple process built entirely on differing vapor pressures. If you have a mixture of A and B, and A has a higher vapor pressure than B, then when you heat the mixture, the vapor phase will contain a higher concentration A than the liquid phase did.
But in modern industrial settings, they don't just boil and condense once, they use these complex vertical columns. Why is that structure so critical for high purity?
The column forces repeated vaporization and condensation cycles. It acts as a cascade of tiny individual Raoult's law separators. Engineers call the effective separation unit a theoretical plate.
And at each theoretical plate, a new liquid-vapor equilibrium is established.
Which means at each stage, the vapor becomes progressively richer in the lower boiling component, moving upward, while the liquid becomes richer in the higher boiling component, moving downward. By creating dozens of these plates, the column can achieve extraordinary purity.
And for substances that might decompose when heated too highly,
they use vacuum distillation. By drastically reducing the external pressure on the liquid, the necessary boiling temperature is significantly lowered. This protects the thermally unstable components from decomposition. It's essential for getting heavy oils and lubricants in the final stages of crude oil refining.
Finally, let's look at the grandest scale of all, how this physics governs the Earth and our own bodies.
Water vapor is the thermodynamic engine of our planet. It is by far the most significant greenhouse gas in the atmosphere.
And on the ground, evaporation acts as a massive temperature regulator.
Absolutely. Evaporation from oceans and lakes absorbs enormous amounts of solar heat, storing that latent heat in the vapor phase, which effectively prevents the surface temperature from skyrocketing during the day. Once that water vapor reaches the upper atmosphere, it condenses on tiny aerosol particles, forming clouds.
And clouds play a double role in climate control.
They do. During the day, they reduce incoming solar radiation, causing a net cooling effect. At night, they trap and release absorbed thermal radiation, which prevents the ground from cooling too quickly. It's a blanket.
We also see commercial uses relying entirely on nature's energy, like large-scale salt harvesting.
Yes, the source highlights the industrial use of solar evaporation to harvest dissolved salts from large brine basins. You simply rely on the sun to supply the enthalpy of vaporization to remove the water, leaving the valuable solids behind.
But the most personal day-to-day application, and the one we started with, is human cooling. Sweating.
The human body is a surprisingly powerful heat engine. An adult at rest generates about 110 watts of heat continuously, and that heat must be released to maintain a constant core temperature.
And sweating is the body's primary mechanism for releasing this heat via evaporative cooling.
It is. The evaporation of water from the skin removes significant heat up to 330 joules per second per square meter of skin. Fine water droplets absorb the necessary latent heat from the blood circulation near the skin as they transition into vapor.
And this brings us back to the core concept of this entire deep dive, vapor pressure. Because the effectiveness of sweating is entirely dependent on the vapor pressure difference between the water on your skin and the surrounding air.
This is the definitive answer to why humidity feels so oppressive. When the air is already highly saturated with water vapor, when the air's saturation vapor pressure is already near 100%, the necessary vapor pressure difference drops close to zero.
The evaporation rate stalls.
It stalls. The rate of escape is less than or equal to the rate of reentry. So the sweat just agglomerates without taking heat away, and you feel sticky and overheated because the phase transition required for cooling has failed.
The wind helps.
Wind helps enormously because it prevents that high humidity layer from building up right above the skin, ensuring a non-equilibrium state is maintained locally. It sweeps the air, keeps the local vapor pressure low, and allows evaporation to continue.
Okay, to bring this all home, our source provides an example of a typical lab experiment. It's determining the vapor pressure curve and the enthalpy of vaporization for pure water and N-butanol using the static isotonoscope we discussed earlier.
This hands-on example validates the entire theoretical framework. The procedure, as we noted, involves carefully using the auxiliary manometer to balance the sample vapor pressure against an external measured pressure across a small temperature range.
And the raw data pressure versus temperature gives us the expected exponential curve, confirming the qualitative shape described by August's formula. But the real insight comes when we apply the Clausius-Clapeyron linear transformation. We are plotting the logarithm of pressure against the inverse of temperature.
And when they did this for both water and N-butanol, the data points form strikingly straight lines. This is a powerful visual confirmation that despite the simplifying assumptions, the Clausius-Clapeyron relationship holds true across this temperature range.
And the power of that linearity is that the slope gives us the enthalpy of vaporization.
For water, the regression resulted in a slope of negative 5103.6 Kelvin. For N-butanol, the slope was slightly steeper, at negative 555 another 0.5 Kelvin. By multiplying the negative slope by the universal gas constant, the experimenters calculated the experimental EVH.
And what were the resulting calculated values?
The calculation yielded median H for water as 42.4 kilojoules per mole, which compares reasonably well to the literature value of 40.6. For N-butanol, the calculated EVH was 46.2 kilojoules per mole, compared to a literature value of 48.4.
So N-butanol consistently required about 4 kilojoules per mole more energy than water to vaporize. Why is that? I mean, water is famously cohesive because of hydrogen bonding.
It's an excellent question. While water has incredibly strong hydrogen bonding, the N-butanol molecule is composed of a polar hydroxyl group, which can hydrogen bond, and a long nonpolar 4-carbon hydrocarbon chain. The forces holding the N-butanol liquid together are the sum of its hydrogen bonds and very significant London dispersion forces from that long chain.
And dispersion forces increase with molecular size and surface area.
Exactly. That longer nonpolar tail creates stronger collective intermolecular attraction forces that must be overcome. So over this measured range, the total cohesive forces of N-butanol are slightly higher than those of water, hence the need for that extra energy to liberate the molecules into the gas phase.
However, we note that the measured values deviate slightly from the published literature values. It's critical to understand why.
Right. We know the approximations built into the Clausius-Clapeyron equation itself contribute. The two main theoretical simplifications are that kVH is perfectly constant across the temperature range, and that the vapor phase behaves as a perfect ideal gas. In reality, neither of those is perfectly true.
And then there are the practical measurement inaccuracies inherent to the lab setup.
Absolutely. The manual setting of the external pressure on the main manometer introduces reading errors. The source estimates about plus or minus 5 torr. There's also the challenge of visually aligning the mercury meniscus, maybe another plus or minus 2 torr. And even the standard lab thermometer itself carries an inaccuracy of around 1 Kelvin.
So these cumulative practical and theoretical errors contribute to the deviation.
Exactly. They add up to the roughly 4% deviation seen in the final calculated enthalpy values. The job of the careful experimentalist is just to minimize these factors.
So we started with the random, chaotic movement of individual molecules, followed the mathematical rigor of chemical potential, and finished with the immense power generation of a steam plant and the crucial temperature regulation of human sweat. It's remarkable how the same simple dynamic, the phase transition, underlies all of these systems.
The key takeaway is the power of that linear relationship, plotting log p versus 1 over t. This graph turns complex, exponential physical behavior into a simple straight line, allowing us to characterize any substance thermodynamically by its enthalpy of vaporization. This single principle links the microscopic forces holding molecules together to the macroscopic energy transfers that define modern engineering and climate science.
So we learned that the linear plot, LNP equals ABT, is the key to finding AVH for a phase transition. Now, here is something for you to mull over. Imagine you are given two such linear equations for an unknown substance. One describing its solid-to-gas phase change, sublimation, and one describing its liquid-to-gas phase change, vaporization. How would you use just those two equations to calculate the exact temperature and pressure of its triple point?
Think about what the condition for the triple point represents: the simultaneous equilibrium of all three phases. What mathematical operation is required when two separate conditions of equality must be met simultaneously?
We hope this deep dive into vapor equilibrium gives you a new appreciation for the physics that governs everything, from the perfect vacuum in a power plant condenser to the steam rising from your morning coffee. We'll see you next time.